Welcome in the fourth lecture of convective heat transfer. In this lecture, we will be discussing about thermal boundary layer. Let me first give you the outline what we will be covering in this lecture. First, we will be starting from energy equation and we will be simplifying this one for low Eckert number cases. Next, we will be presenting the idea of thermal boundary layer over a flat plate. Then we will be examining the order of ratio between the thermal and velocity boundary layers using scale analysis, and at the end we will be discussing the case of high and low Prandtl number fluids along with the Nusselt number correlations. So let me start from the previous lecture endpoints. In the previous lecture we have discussed about thermal energy equation. So thermal energy equation we have derived two forms. We will be starting from CP form and we will try to non-dimensionalize that one using different parameters. So in this equation you can see in the left hand side we are having convection, right hand side we are having the compressibility term, and then we are having the conduction, and finally the viscous dissipation phi. So first let us see what are the non-dimensional parameters we are going to use. For density, we are using rho star equals to rho by rho naught. Rho naught is the characteristics density, let us say. For time, we are using T star equals to time t by L by V naught. So V naught is the characteristics velocity and L is characteristics length. Then dimensionless velocity, as I have already told, V naught is the characteristics velocity, so this is U bar by V naught. For temperature, we are using theta, so theta is nothing but T minus T naught, which can be talked as reference temperature, and delta Tc is the gradient of the temperature. For spatial derivatives, we know spatial derivatives are coming over here as del. So del can be non-dimensionalized as del star. So del star will be del by L, capital L. So that means del del x will be 1 by L into del del x. For pressure, we are using P star equals to P by rho naught into V naught square. So with these non-dimensional parameters, let us reduce this equation. So if we substitute all those non-dimensional parameters in equation 1, what I have shown you in the previous slide, so we get this type of equation. So for the convection term, you see we are having rho naught into rho star after non-dimensionalization. T became theta, so as a result delta Tc came over here. We are having del del T and del over here, that gives rise V naught by L over here, and in the right hand side for the conduction term we are having K delta Tc by L square. For del P del T term we are having rho naught V naught square over here, and for del del T we got V naught by L, and for viscous dissipation we are having V naught square by L square. Okay. Beta T came over here, which was earlier in the equation number 1. Then let us divide the equation throughout by this term rho naught Cp delta Tc V naught by L. If you do so, then you will be finding out the equation is simplifying in this fashion, where left hand side is convection, right hand side we are having conduction. This is the pressure gradient term, total derivative has been expanded over here, and this is the viscous dissipation term. Okay. Now let us try to find out where we are having non-dimensional numbers in this equation number 2. So first let us see what are the different non-dimensional numbers we use in heat transfer analysis. So in case of heat transfer, first comes the Peclet numbers, which is nothing but the ratio between the advection heat rate and the diffusive heat rates. Okay. So it can be written as L V naught by alpha. Alpha is your thermal diffusivity, which takes care about the advection and diffusion heat rates. Okay. So here you see we have reduced this L V naught by alpha in terms of L V naught by gamma and gamma by alpha. Gamma is your kinematic viscosity. So here the first part of this equation comes out as Reynolds number, because we know Reynolds number is L V naught by nu, and then here it is nu by alpha, which is nothing but your Prandtl number. Okay. So we can write down Peclet number is equals to Reynolds number into Prandtl number. Then another non-dimensional number we will be introducing over here, which is nothing but Eckert number. Eckert number gives you the inertia to the enthalpy drop ratio. Okay. So here Eckert number is V naught square by Cp into delta Tc. Okay. As we are using Cp form, Eckert number will be very important. Okay. So here you see in the equation, if you see minutely, here we are having V square by Cp into delta Tc. So we can write down Eckert number here in front of this pressure gradient term. Okay. Then if we look at the viscous dissipation coefficient, so viscous dissipation coefficient is nu V naught by L Cp into delta Tc. So that can be reduced as V square by Cp into delta Tc, which is nothing but the Eckert number, and nu by V naught by L, which is nothing but 1 by Re, okay, which we have introduced over here. L V naught by nu is equals to Re. So this coefficient can be written as Eckert number by Re. So we have seen that different parameters can be written, different coefficients can be written in terms of the non-dimensional numbers. So if we put all these non-dimensional numbers, then we get this equation. Okay, so here you see we are having 1 by Rep here, which is nothing but Peclet number. Here we are having Eckert number, and here we are having Eckert by Reynolds number. For beta t, we are doing this type of approximation. From theta non-dimensionalization, we know theta is nothing but t minus t naught by delta Tc. So t minus t naught by delta Tc can be reduced in this fashion, t equals to t naught plus delta Tc into theta, and beta t can be written as beta t naught into 1 plus delta Tc by t naught into theta. So if you replace this beta t in terms of this, so this coefficient comes over here, right? Next, let us see what happens whenever we are having very low Eckert number. Okay, this is our objective, to see that what happens to low Eckert number. So low Eckert number means low kinetic energy and significant temperature drop. Okay, Cp into delta Tc will be becoming very big. So in that case, we get the equation little bit modified. So this term and this term can be neglected because low Eckert number we are having. And if we consider that we have chosen rho naught in such a fashion that density, non-dimensionalized density rho star becomes 1, then this equation 2 is actually reducing to this form. So rho star becomes 0, and these two terms can be neglected compared to the others. So we get this simplified equation, where in the left hand side we are having convection and in right hand side we are having conduction. And as non-dimensional number we are having Reynolds number into Prandtl number. Okay, so this is very, very important equation. If we see the corresponding dimensional form of this equation, so it will be becoming left hand side, it is nothing but convection, rho naught into Cp into del t plus u dot into delta t. So this is the convection term, and the right hand side we are having k into delta square by t. So this part is coming from here, so this is convection term, right? So let us now see from our knowledge of fluid mechanics, because this is the prerequisite of this course. So from the fluid mechanics knowledge, we know what is hydrodynamic boundary layer. This figure is very known to you. So we are having a flat plate. Okay, so this is the flat plate, and a free stream fluid flow is coming over here having velocity u infinity. Let's consider this is our x direction, streamwise direction, and this is our cross streamwise direction y. Okay, so you can find out that immediately whenever the flow is coming in contact with the solid surface, so there the velocity will be becoming 0 due to no slip condition. So here velocity becomes 0 everywhere. Okay, and far away from the surface we will be having once again no resistance, so this will be your u infinity velocity. Okay, so there will be a velocity gradient, and we know from our fluid mechanics knowledge that this is a parabolic profile. Okay, and if you see that where this velocity is becoming 99% of the free stream velocity, that limit we can call as hydrodynamic boundary layer. So here I have shown the hydrodynamic boundary layer in this fashion. So this is already known to you from your fluid mechanics knowledge. Now let us see what is our thermal boundary layer, okay, which is the part of this course. So in case of thermal boundary layer, we will be taking the similar type of flat plate. Okay, so this is the flat plate. Let's say the characteristics of this flat plate is having temperature Tw. Okay, a free stream fluid is coming over the flat plate having temperature T infinity. Okay, and you see Tw is higher than T infinity. For this case we have considered. So whenever the fluid is coming in contact with this hot plate, so immediately the adjacent layer of this plate will be becoming very high temperature. Okay, so here we are having very high temperature, and away from the surface we are having similar T infinity. So there also we will be having a temperature gradient, and this temperature slowly will be tending towards this T infinity. And at a point where temperature becomes 99% of T infinity, okay, we can call, so this is your thermal boundary layer thickness, okay, delta T. So if you continue finding out those points which is having 99% of the free stream temperature and join those like this, so that is the locus of those points, which is nothing but your thermal boundary layer. So just like your velocity boundary layer, you can have thermal boundary layer, and just like your velocity boundary layer thickness, we can have the thermal boundary layer thickness. Okay, so this is very important concept. So thermal boundary layer you can see over here. Next, let us see from thermal boundary layer point of view. We have earlier derived this equation, non-dimensionalized energy equation, for low Eckert number cases. Now let us try to see over here what is the ratio between the left hand side and the right hand side. Left hand side we had the convection, right hand side we are having conduction. So convection to conduction, which is nothing but the Peclet number, advection to diffusion, which is nothing but Peclet number. So it comes as REPR into del theta by del T plus U star into del theta, which is nothing but your convection term, and in the conduction you are having del squared theta. Now we know that Peclet number is nothing but RE into PR. Okay, so what we can see over here, if convection is of the order of conduction, then we can write down Peclet number is of the order of REPR, because this will be of order of this one. Okay, so convection is of the order of conduction, so Peclet number will be becoming order of RE into PR. From our velocity boundary layer knowledge, we know that Reynolds number inside the boundary layer region, where inertia and viscous forces are more or less comparable, the Reynolds number will be of the order of 1. Okay, so RE is of the order of 1. So, but outside the boundary layer, obviously RE will be very large, but inside the boundary layer region, RE will be of the order of 1. Now, if you try to find out the ratio between the thermal boundary layer thickness and the velocity boundary layer thickness or hydrodynamic boundary layer thickness, so it will be depending on only Prandtl number, because here we have found out RE is of order of 1. So ultimately this Prandtl number actually defining that what will be the ratio between the velocity boundary layer and the thermal boundary layer. Okay, so delta T by delta is actually a function of Prandtl number. Now let us see that what happens for two different cases where thermal boundary layer dominates, and then we will be seeing where velocity boundary layer dominates. So first we will be seeing a thick thermal boundary layer cases where delta T is very higher than delta. A schematic representation I have shown over here. So here you see this is our velocity boundary layer. Okay, so at this point the velocity of the fluid stream is becoming almost 99% of the free stream velocity. And here this is our thermal boundary layer. Okay, so this is the locus of all those points where temperature is becoming almost 99% of the free stream temperature. Okay, but here one important thing is here that delta T is higher than the delta. Okay, now in this case let us try to see that what happens in this comparison. So from the figure we have already shown delta T is much larger than delta, and we can write down that delta T by delta is actually greater than 1. Now if we take the plate very long, so it is a very long plate, let us say L is very high, so delta T by L is actually less than 1, and delta by L is less than 1. Okay, L is significantly large. Now let us see for 2D convection diffusion equation, forget about 3D, so we are thinking about 2D problem over here. So this will be your conduction term, and this is your convection term. Okay, now let us see the scale of both the cases. Okay, so if you see the scale, so in conduction term we are having alpha into del square T del x square and del square T del y square, and in convection term we are having this one. Okay, so individually if you try to find out the scale, so alpha remains over here for the first term, delta for this T we will be having delta Tc, and for this x we will be having L square, because x is the streamwise direction. Okay, and for the second term we will be having alpha delta Tc, and for y, which is actually the perpendicular direction, our length scale is delta T, which is nothing but your thermal boundary layer thickness. Okay, so if we compare between these two, as L is much larger compared to delta T, so this will be the dominant term. Okay, so our conduction will be of the order of alpha into delta Tc by delta T square. Similarly, if we do for the convection equation, by the way, before going to the convection equation, let us see the continuity equation first. So if you see the continuity equation, we know from fluid mechanics, so del u del x plus del v del y is equals to 0. So from there we know that order of the first term del u del x will be becoming u infinity by L, and the second term will be becoming v naught by delta. Okay, so if we equate and try to find out what is the order of this v naught, So we will be finding out V naught comes out as u infinity delta by L. Remember here for y direction we have taken actually velocity boundary layer thickness delta. So once we find out V naught, we can now get the order of the convection terms. So here the first term becomes u infinity delta Tc by L, and second term becomes, for V we are taking V naught, so V naught into delta Tc by delta T. Remember for here we have taken delta T for the perpendicular direction. Now this V naught, as we have already found out in terms of u naught, let us try to reduce this. So in place of V naught we have put u infinity delta by L from here, okay, and if we find out, this actually becomes u naught delta Tc by L, which is this term, multiplied by delta T. Now we have considered initially that delta by delta T is actually very small quantity. Thermodynamic boundary layer actually dominates over the velocity boundary layer. So in this case we will be finding out that this term is actually becoming the dominant term for the convection. Okay, so this is lesser, this is greater than this one. Okay, so this term becomes, this term becomes the greater term compared to this one. Okay, so our convection becomes of the order of u infinity delta Tc by L. Okay, conduction already we have told alpha into delta Tc by delta T square. So from the equation, if we see the scale analysis from both the sides, we can have a comparison between the scales of conduction and convection, and if we do so, then we are finding out this was my convection and this was my conduction. Okay, so from here we can get that delta T square, after reducing from here, cancelling out delta Tc from both the sides, we get delta T square is equals to alpha L by u infinity. Okay, so we know that alpha by u infinity L is becoming 1 by Peclet number. So what we have done, we have divided this whole equation by L square, so we get delta T by L whole square is equals to 1 by Peclet number, right. Now we can write down delta T by L is of the order of 1 by root over of Peclet number or root over of REPR. From velocity boundary layer, we have already knowing that delta by L, which is hydrodynamic boundary layer by the streamwise length scale, is actually Re to the power half. Okay. Now if we merge these two equations, then we can get the ratio between delta T by delta. So if we do so, we get delta T by delta is of the order of Prandtl number to the power minus half. Earlier also we have told you, we have shown you that this ratio between the thermodynamic boundary layer and velocity boundary layer will be becoming function of Prandtl number. Here also we are seeing so, but the order is something like this, Prandtl number to the power minus half. Now at the beginning we have considered that the thermodynamic boundary layer actually dominates, so delta T is higher than delta. Okay, so this ratio actually is greater than 1. So that means what we have found out, Prandtl number to the power minus half is actually greater than 1. This is the case where Prandtl number is very small. Okay, so for satisfying this one, Prandtl number needs to be very small. So Prandtl number very low, then only we will be getting that thermodynamic boundary layer has actually dominated the velocity boundary layer. Okay, so therefore for low Prandtl number fluid, thermodynamic boundary layer thickness is higher than the hydrodynamic boundary layer. So if we try to see the heat flux, so in this case, so let's say the heat flux is, wall heat flux is QW. So if we try to find out that what is happening in case of the heat flux, so QW heat flux is nothing but from the conduction we can write down minus K del T del Y at Y equals to 0, because here near the plate the conduction dominates, and immediately adjacent to this plate we are having fluid layer which is having the convection. So from convection we can write down H into TW minus T infinity. So from here we can get H, heat transfer coefficient, is nothing but QW by TW minus T infinity. Okay, so QW from here we can see is of the order of K delta T, and Y del Y will be coming as delta T. Okay, so delta Tc by delta T, so this is the order of the QW, right. So if we put in this side from these two equation of this order, then heat transfer coefficient we find out in the order of K by delta T. Okay. And if we try to see what is the Nusselt number is a non-dimensional number which gives rise the convection to conduction resistances. So Nusselt number is HL by K. So from this equation we can find out what is HL by K, and from the order analysis whatever we have found out over here, H is the order of K by delta T, we get Nusselt number is of the order of root over of REPR. Okay. So in case of low Prandtl number fluid, we have got Nusselt number is of the order of REPR. Okay. Now let us see the other horizon, that means thin boundary layer thickness, that means the velocity boundary layer will be actually higher. Okay, delta is higher compared to the thermal boundary layer thickness over here. So this is the thermal boundary layer over here, and here this dotted line shows the velocity boundary layer. Okay, corresponding temperature profile and velocity profiles I have shown over here, right? Now let us see this horizon. So as we have considered delta is higher than delta T, so delta is higher than delta T, so I can write down delta T by delta is actually lesser than 1. Okay. So if L is significantly large, then we can take delta T by delta is smaller than 1 and delta by L is smaller than 1, and in this case we will be going for Taylor series expansion. So if we do the Taylor series expansion for U, we can write down in this way. Okay, so U is nothing but U plus Y del U del Y plus half into Y square plus del U square del square U del Y square plus so on the higher order terms. Okay, now here at the wall we know for no slip boundary condition it will be U at wall y equals to 0, it is 0. So this term can be cancelled. Okay, so we get U is actually of the order of y into del U del Y into del U del Y if we neglect the higher order terms. Okay. Now let us take this del U del Y is equals to A naught. Okay, so from fluid mechanics we know this del U del Y is nothing but tau W by mu, where tau W is the wall shear stress. Okay. So we can write down U equals to A naught into Y. And finally if we try to find out the order of U, so which is nothing but U infinity delta T by delta, and here delta T by delta comes as ratio between the thermal boundary layer thickness and the velocity boundary layer thickness. Okay. Then if we try to use continuity equation, so from continuity equation we have written del V del Y is equals to minus of del U del Y. This will be going in the other hand side, so that is the continuity equation. So del U del X I can write down as U is equals to A naught into Y. So del U del X will be becoming d dx of A naught and Y will be coming as free. Okay. Now if we try to use the Taylor series expansion for V, just like the U as I have shown in the previous slide. So here you can find out V into Y into dV dy plus half into Y square into del square V del Y square and so on. Okay. Now if we use no penetration, so once again you can find out that this term becomes 0 at the wall. Okay, because no penetration will be there. If it is porous, then other cases will happen, but as it is no penetration, so this term will go to 0. So we find out V is becoming Y into del V del Y. Okay, if we neglect the higher order terms, and already we have shown del V del Y is nothing but minus of d dx of A naught into Y. So we can write down minus of d dx of A naught into Y square, right? So if we try to see the order of this V now, so it becomes for A naught the order will be something like U by L, so U by delta. Okay, and here this X is coming as L and Y, as we are talking about thermal boundary layer thickness, so Y comes as delta T square. So remember, whenever we have considered this Y, so this is replaced by delta, and whenever we have considered this Y, it is replaced by delta T square. Okay. So V becomes of the order of delta T by delta into U infinity multiplied by delta T by L. Okay. Now if we see the convection term for this case where hydrodynamic boundary layer dominates, so in this case the convection terms takes the order of this one, delta T by delta into U infinity into delta Tc by L for the first term. U is of the order of this one, here we have shown, and it is becoming delta Tc by L. Second term V is becoming of the order of this one, so this we have put over here, and delta Tc by Y became delta Tc by delta T. Okay. So this is of the order of the second term, this is the order of the first term. So both are same, so convection term will be taking this order. Okay. For conduction term, here you see this is the order of first term alpha into delta Tc by L square, because X we are having, so this is L, and for this y we have taken delta t square. Now we know delta t is smaller compared to L, so this will be the dominant term, okay. And once again this is the dominant term, so this is the order of the conduction term. So once again if you equate conduction and convection, so you get this type of scale analysis. So from here we can obtain delta t cube is actually alpha delta L by u infinity, okay, of the order of. So from here if you do little bit multiplication and modification, so you can get delta t cube by L square delta is of the order of 1 by REPR, okay. Just from this one it will be coming, okay. Now you see already we know that what is the ratio between delta by L, okay. If you just little bit rearrange this one, so this can be delta t by L whole cube and here delta by L. So this delta by L already we know from our velocity boundary layer concept, okay, which is of the order of 1 by Re, root over of Re, okay. So using this two we can get delta t by L whole cube comes of the order of Re to the power minus 3 by 2 Prandtl number to the power minus 1, okay. So delta t by L comes out as Re to the power minus half and Prandtl number to the power minus 1/3, okay. Now if we compare between these two, then we can get delta t by L becomes Prandtl number to the power minus 1/3, okay. So in this case where velocity boundary layer actually dominates, for this case we have obtained this one. Now we already know that delta t by delta is actually a smaller term than 1, so this equation needs to be satisfied. Prandtl number to the power minus 1/3 less than 1 needs to be satisfied. So this only can happen whenever we are having large Prandtl number fluid, okay. So for large Prandtl number fluid we are having delta greater than delta t. So once again if we try to do the same analysis of heat flux, so we can get heat flux is equals to conduction and convection equation just like the previous case. So H becomes QW by TW minus T infinity. If we go for the order analysis of QW, it comes out as K delta Tc by delta T, and for the convection term it becomes K by delta T, okay. If we find out the Nusselt number, so Nusselt number becomes in terms of Reynolds number to the power half and Prandtl number to the power 1/3. So remember this Nusselt number comes out for a large Prandtl number fluid, okay. So let me summarize that what we have learnt in this. So we have actually derived the energy equation for low Eckert number cases. So this equation we have derived for low Eckert number cases by neglecting two terms over here, okay, for pressure gradient and the viscous dissipation. And we have expressed the thermal boundary layer thickness using scale analysis, okay. So for low Prandtl number fluid we have found out it is of the order of Prandtl number to the power minus half, and for large Prandtl number fluid we have found out this is of the order of Prandtl number to the power minus 1/3, okay. And we have obtained the Nusselt number functions, Nusselt number correlations in terms of Reynolds number and Prandtl number. For thick thermal boundary layer we have found out Nusselt number is of the order of root over of REPR, and for the thin thermal boundary layer compared to the velocity boundary layer always Nusselt number becomes of the order of root over of Re into Prandtl number to the power 1/3, okay. So these things we have actually understood in this lecture. Now let me test how far we have understood this topic. So we are having three questions over here. So first question goes like this: in case of thick thermal boundary layer, express the order of the convection term, okay. So order of the convection term already I have discussed in the lecture. Four options we are having. So if you go back to the discussion in this lecture earlier, so you can find out the correct term is this one, U infinity into delta Tc by L, okay. Second question, thermal boundary layer is thicker for fluids having four options we are having: high Prandtl number, low Prandtl number, high Eckert number, and low Eckert number and low Prandtl number fluid, okay. So already we have seen that first assumption we need to take is low Eckert number, and second assumption obviously for this thermal boundary layer thicker required is Prandtl number, okay. So both the cases needs to be satisfied, so this is the answer, okay. For the third one, for thin thermal boundary layer, which expression is correct? So I have given four expressions for the Nusselt number, and last one is obviously none of the above. So if you see minutely, the correct answer is this one for thin thermal boundary layer, okay. So Nusselt number is of the order of Re to the power half and Prandtl number to the power 1/3, okay. So thank you. At the end of this lecture, please visit our next lecture, which we will be discussing about low Prandtl number over a flat plate, okay. And if you are having any question, please keep posting in our discussion forum. Thank you.